Okay, for now, let's just assume that we are using a Monte Carlo approach to evaluate Q values for a specific policy. So we can combine a Monte Carlo approach with what we saw in the previous lecture with the policy iteration, right? We saw how we can use the policy iteration approach to converge on the optimal policy. That is, we choose an initial policy, we compute the Q values or the state values. So the state values is more appropriate in the offline case, but here it's better for us, it will be easier for us to actually learn the Q values. In the Monte Carlo approach, we won't go into the exact details, but I'm sure if you think about that, you can understand why this is the case here. And then, once we have the Q values, we can update our policy towards a better policy and continue this process over and over again, right, in iterations. So, let's see how that would work. That actually will not work very well in the online case, right? Unlike the offline case, and I'll show you why in a second. Okay, let's see the problem through an example. So let's assume that again we're solving a grid world, the grid world here on the right. The state space is U, W, X, Y, and Z. These are the different states that our robot can be in. And the action space is well, the four cardinal directions and the action exit in one of the terminal states that are U, Y, and Z. These are the terminal states. You can only perform one action there, which is the action exit. The reward function is as shown here on the actual grid. You get a +1 for exiting in U, +10 on Y, and -1 on Z. Okay, so let's do policy iteration with Monte Carlo Q estimations. So we need to start from some initial policy. So let's assume that we're using this policy here. This is our first policy, and we'll update it over time. Right, it provides us with an action for each one of the states. The states are listed here on the left. So for instance, for state U, we're going to perform the action exit. And our current Q estimations are, let's say we initialize them to 0 for non-terminal states. Actually, for all states, for all state action pairs, we'll just initialize our Q values to 0, right? NA represent actions that are not applicable in some of the states, right? So for instance, in state U, you can only take the action exit. So that's the only Q value that is available here. Okay, so let's start doing policy iteration. We start with a policy evaluation phase. Okay, so we'll try to evaluate our Q values. And we'll do it using a Monte Carlo approach. Okay, so let's sample a trajectory, and this is the trajectory that we sampled. Our robot went right, and then it went up, and got an immediate reward of -1. And so let's assume a discount factor of 1, just for simplicity. Okay, so no discounts. So now we observed a capital G value of -1. So we'll update all of the Q values along the way that we just sampled to be -1. So for instance, the Q value for being at location X and taking action up, north, would be -1, right? So this is the value here. Good, so we update our Q estimations. And let's now do a policy update step. Okay, so we're doing policy iteration. Let's update our policy based on these Q values. So based on these Q values, now it is better for us at location W to go W. Oof, I have some overload. So at location W, it's better to go west, right? Because it has a Q value of 0, as opposed to going east, which has a Q value of -1. Okay, so I update the policy to go west on state W and east. We don't want to go north at state X. State X, we want to go, instead of north, we want to do something else. Let's say we just do east at location X, right here. Okay, so we update our policy. Let's sample another trajectory and update the Q values. So we sampled another trajectory, and our trajectory simply goes left, goes east, goes west at our initial state W, and gets to the +1 reward. So now we update our Q values, right, for going west on location W to be 1, and our Q value for exiting at location U, at state U, to also be 1. Now we updated our Q values, and we'll do another policy update step, right? But what happens now? Actually, once we did that, we converged on a local optimum. Okay, so we won't change our policy. And now we might ask ourselves, 1 second, so didn't you say in the previous lecture that once we did policy iteration and converged on a policy, our policy didn't change, then it must be the optimal policy? I did say that, right? And clearly, this is not the optimal policy, because you can go east, right, and get a reward of +10. So my claim regarding convergence was for the offline case, when we are able to sweep over, when we update our Q values, our state values, over the entire state and action space, like we do a full sweep in the offline case. But this does not hold for the online case, right? For the online case, it doesn't hold if we sample if we look only at a small portion of the state and action space, where we update the Q values for, or we actually sample these in a specific trajectory. That is, we have to, in order to guarantee convergence to the optimal policy, we have to explore the entire state space. We have to do a full sweep, and in an online method, this means that we have to explore the entire state and action space with some probability, right? Non-zero probability. So we have to inject exploration into a policy iteration process. Well, any policy iteration process, if we're using a Monte Carlo iteration or not. Right? At the end of the day, we will need to introduce some exploration. So how can we introduce some exploration? So usually what we do is, instead of using what's called a hard policy, a policy that for each state has a specific action that you always take, we introduced soft policies. Soft policies define a distribution over the action space. So they define a probability for taking each one of the actions in a specific space. So in a specific state. So given a specific state, there is some non-zero probability of taking any of the actions, right? And this will ensure that visiting every state action pair has a non-zero probability, as long as they are reachable, of course. Right? And now a soft policy is a mapping between state action pairs to some probability value between 0 and 1. Some soft policies can be defined differently in different algorithms. They can also map from a specific state to a distribution, sometimes a parametric distribution. This is specifically the case for continuous control problems. Right, so this definition here is mostly relevant for discrete action spaces, but we can adjust it to apply to continuous action spaces by mapping state to a distribution over actions. We'll see this later on, don't worry too much if you don't understand it now. And at the beginning, actually at every point of time, we would like to have the probability of taking each one of the actions at any states to be larger than 0. Commonly, we start with a more uniform distribution initially, where we incentivize a lot of exploration initially, and over time we would like to reduce these probabilities for those actions that are less optimal, let's say, that we produce that are affiliated with lower Q values, and increase the probability of taking the more promising action. So gradually we shift not to a deterministic policy, but towards more of a deterministic policy, okay? Also known as low entropy policies. We'll define entropy and discuss it later on. That's it for now. Let's again we'll dive deeper later on. For now, that's sufficient. So let's see an example. So for example, we can apply epsilon greedy approach here, where we select a random action with probability epsilon, right? So with probability, so for every action in our state space, we have a probability of epsilon over the size of the action space to be selected. Else, with probability 1 minus epsilon, we select the greedy action. So the action that has the highest Q value so far, right? It might change over time, but the greedy action is the one that currently we believe to be the best action. Okay, so the probability of selecting the best action is 1 minus epsilon plus epsilon over the size of the action space, because with probability epsilon we might still select the greedy action. And so this leads us to the, now we have everything that we need in order to define our first reinforcement learning algorithm, which is on policy, first visit Monte Carlo control for epsilon soft policies. And the algorithm is given in the following pseudocode. This is also from our textbook. And it works as follows. We first initialize for every state and action pair our tabular estimation. So we can initialize the Q values arbitrarily. We keep the average returns, these are the capital G values, as an empty list. Later on we're going to average those in order to get an estimate of the Q value for each state and action pair. And we start with some arbitrary epsilon soft policy, right? So our policy now is a soft policy in order to ensure sufficient exploration. And then we repeat forever, where we generate an episode using our specific policy, the current policy that we have. And for each state and action pair appearing in the episode, we compute the G value, right, the return. And we store that in our set of returns. And we set our Q estimation based on the average returns that we've seen so far. Next, for each state in the episode, we compute the best action, the greedy action, given our current Q estimations. And then for all of the actions in the state, we set a specific action based on the epsilon greedy approach, on the epsilon soft policy. With some probability we take the greedy action, else we take the random action. Okay, this is important in order to guarantee sufficient exploration. To repeat forever, we are guaranteed to arrive at an estimate